Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode, you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media.
Today's episode is sponsored by Block Engineering, a manufacturer of widely tunable mid-infrared lasers based on quantum cascade laser technology. Block's lasers are designed for spectroscopy, imaging, and other applications that require highly precise and stable illumination with flexible programming. Please visit www.blockeng.com for more information. The episode is also sponsored by Zimia, your #1 camera manufacturer for industrial, commercial, and scientific applications, creating the best innovations in the market. They specialize in unique custom and off-the-shelf solutions for every need. Visit www.ximea.com today.
In our flagship magazine, Photonic Spectra, we have a section that looks back at the innovations that appeared in previous issues 5, 10, 20, and 30 years ago. Typically, when we get to 20 and 30-year marks, we're looking at research advances that are just now hitting the market as products or services. Coincidentally, when we reached out to today's guests, they noted that they saw their work pop up in that very section. About 20 years ago, Hongxing Jiang and Jingyu Lin invented the MicroLED. While the technology did see commercialization between then and now in the form of automobile and industrial lighting, the dream was to see the technology be applied to displays. If you're looking for a new TV this holiday season, you may have noticed that the top of the line isn't just populated with OLED models. While manufacturing challenges still remain, microLEDs offer a wonderful marriage of efficiency, brightness, and sheer possibility. In today's conversation, we'll explore that marriage. Up next, news editor Joel Williams speaks with Professors Hongxing Jiang and Jingyu Lin, co-directors of Texas Tech University's Nano Photonics Center. I'm Don McQuista, Department's editor for Photonics Media, and you're listening to All Things Photonics.
While micro-LEDs are, still something of an emerging technology, and sorry to bring up the number, but it's been about 23 years since the research that first realized them. Can you tell us a little bit about those early years of work, what led to the development, and some of those early applications of micro-LED technology?
Okay. We were working on nitride, and specifically, we were working on some kind of called the photonic structures or nanostructures. So there was one question, and what happened if we make these big LED, typically 300 micron by 300 micron, if we reduce to a very small size? Is any physical property will be changed? Is any performance will be changed? That was originally how this came from. And so we decided we're going to try to make one. But for gallium nitride, particularly early time, and P-type of materials was issued, and the contact resistance will be increasing as the size becomes smaller. So it takes some time to play around to improve the performance, and eventually, and we find, and this can be done. So we demonstrate, I think, the first one, and 2000. And with size about 12 micron, it looks bright, and the blue colors will get very excited.
Yes, I guess. In fact, there's some other additional challenges we face, I guess, was like etching. That was like went back to early 2000s, etching gallium nitride was not that trivial. To also, we need to overcome certain surface damage. You need to really optimize how you control those processes. In order to get the light from a very small size gallium nitride micro-LED, we called at that time, we called the micro disc LED, in fact. So that was not that trivial. So we were very, very excited. Went back to very early, 2000s, we see the light coming out from under microscope. It was really bright. So that was a very amazing feeling, yes. Mm-hmm.
Yeah. When we get this first microLED and we both are physicists, we're kind of interesting to as anything new comes up, we just by reducing the size. And we find it quite interesting. And a few things is very to the advantages of these ALD used as a lighting or display. And one thing is, its efficiency is become increased per unit area compared with all the big ALDs. And second thing is, you find that these ALDs, the turn on, turn off speed also increase. So these are very important properties. And today for all these application, AR, VR, 3D, because you need a very high speed of the displays.
Yeah. So the early applications you were referring to, I think after we kind of realized, in fact, because compared to other traditional three fives, three nitrides, we actually grow on sapphire substrate, which is highly electrically insulating and also transparent. So we figure out that maybe we could actually, with micro LEDs on chip, arrays of them, or maybe we can do something interconnect on chip to making like early applications, which include something we call the interconnected LED, micro LEDs on chip. We get a lot more light. That was one of the big applications when we get down to like a deep UV region, which extraction efficiency becomes a huge problem. And then the other one we talk about is it's become very important one, right? It's connected micro LEDs in series on chip. They can handle high voltage, AC voltage. And this is the Hongxing name right after we call high voltage AC DC LED. So that's what was early applications that we actually did very well in terms of the IP positions. Yes. Mm-hmm.
Yeah, this is the beginning, and when we start to work on this ALD, we were thinking one question. We already have an existing infrastructure, 110 volts AC, and we're going to have ALD to replace all these light bulbs. Are we going to add a DC 3 volts for the ALD lighting, or we are going to use the infrastructure we have, the ALD have to work on for the high voltage and AC? So that question brings us to this called AC LEDs. So we're connecting series for the one string, another string is reverse. So you have the AC and high voltage, and we can plug in our LEDs and direct to the power outlet. That was the first products, real products, and we invented from this micro LED. It's quite exciting.
It's on chip. It's not like Christmas tree out. Connect them outside, So this was really a big advancement in terms of the use of those. People also they use the similar, adapt this to mini LED too, right? They connect the mini LED on chip or flip chip bounded to other outside circuits. So the way approach we did was like adopted pretty widely. Yeah.
Excellent.
Yeah.
Can you tell us a little bit about the path to commercialization? Aside from displays, micro LEDs have seen a lot of use in solid state lighting and in automobile lighting. Tell us a little bit about that journey and how you find a balance between business and research.
We're doing the research, and we always get very interested to make some real products. So as I mentioned, this ACL for both for the high voltage noise for the lighting, and for the DC relative low voltage 12 volts, and these for the headlights of the car, and all these are can commercialize a pretty big in the market. So we find we really did something and important to the society, and will help to reduce the energy and using all these kind of things. And in the process, and we find we try to find some real applications from the kind of research we are doing.
Right. So these are like AC-LED, high voltage, high AC-LED or DC high voltage LED. We thought it's more like a byproduct of our micro LED research. So we were really interested in making like a micro display. Went back early 2000s, as you see some of the applications we had. The first one we made, we tried to like put in the wires down in the circuit and connect each micro LEDs on chip, then put the pads on the periphery of the arrays to make a passive micro LED. So we did drive the micro LEDs in 2000. The micro display, right? First one was published 2011. So we can actually already display characters. We see those. It's incredibly different from the LCD display, for example, even OLEDs, the brightness, the speed, everything. So at that time, we know it's potential for the self-emissive display technology. But at that time, we don't know how to drive the micro display array like in the active mode, which means you really need to drive them by CMOS circuits. Each pixel has its own driver. So we didn't have that until we 2001, 2009. So we had the funding from Army Night Vision. They gave us like a kind of approval to go for to develop that. So that was a very exciting development. We made an active driving micro display for the Army Night Vision goggles. That was actually the original thing. That's really something we would like to pursue. Went back to 2000s. Yeah.
So for the micro display, the concept was demonstrated 2001 and not the 2011 as the Chinese mentioned. And we made one 10 by 10, and because we don't know how to drive this, so we connect this 100 micro LED with 100 wire bonding outside. But that's very clearly and shows up some of the very unique and properties. Very bright, very high resolution, and color is excellent. So all these important or interesting characteristics of these micro LED that we know claim it was demonstrated in 2001. But we understood, and in order to get this really close to the real products, we need to make one probably at least close to the 500 by 500 arrays. But now you cannot do wire bonding. And then we thought about this, and we realized we needed to have a CMOS to drive it. And it took us about 10 years until 2011. And with colleagues together, and we designed the CMOS array, and we demonstrated this, we call the EGA format, which is the 640 times 480, is almost a quarter of the million and pixels. It's a real display. We can see imaging, we can see video playing, just one single color, either blue or green. I think from that work, 2011, and then a lot of big companies, and they realize, oh, this can be done, at least for the single color, and the company can do better than us overall in terms of products, and already demonstrated. I think this started to kick off and all the micro LED field.
Yeah.
Awesome. Now, sort of as a display technology available to consumers, micro LEDs they seem to only have really hit the market just a few years ago. When I was reading up on this work, I noticed Sony had demonstrated a micro LED TV back in 2012. But it seems to have only been made commercially available just a few years ago in 2019. What's made it difficult to commercialize and to produce these displays? You mentioned the very small size of the first displays. Can you talk a little bit about why that is? Why micro LEDs are maybe better suited for smaller displays, at least initially?
I mean, these days for the display, they're getting better and better. But for the nitron micro LED, and these are in terms of the brightness, and these are using for the lighting, so these are very high bright. And then you're talking about the color, and you can control all the colors better than all other existing displays. And then talking about the spatial resolution, because these are small size. And then you're talking about the speed, and now we're talking about the 4K, 8K, micro-LED. It's faster than any other emitters. With all that, now first let me talk about the one difficult thing from the Sony. And I think Sony is the first company that demonstrated the micro-LED large TV, and they targeted in the beginning, targeted the whole panel is fabricated together. You can think about, you get the tens of millions of the micro-LEDs, you get a few wrong, and then you need to fix them. So this technology evolved. And later on, in the Samsung and find, instead of make a huge, bigger panel as a one single TV, and they break it down to the small panels. So each panel maybe and covers 100,000 LEDs, and then make sure each panel works, and then combine the panel and to make a bigger TVs. So this technology has been adopted now these days, and the size is not an issue anymore. You just combine more and more these small panels. You can make a TV for the micro-LED as big as you want. So this is I think it's a very smart move, and to help to increase the yield, overall yield, and for the TVs. So then there's another problem. You got tens of the millions of the LED. They have to put in the right place and with the contacts. So this was extremely difficult, particularly in the beginning. But there's a lot of progress, and right now, and there's some kind of infrastructure has been built up for this micro-LED technology. And one, for example, is a specially designed instrument, and you can call the mass transfer and the millions of the micro-LEDs from wafers and to these bigger panels. And a lot of progress, now you can do it more efficient and much more and accurate. So I think it's already shows up, and these costs also will come down relatively quick if we can transfer very efficiently.
I think the announcement for Samsung is the price already went down to 50K for the very big TV. In contrast to Sony, that one was like 1.2 million, right? So you can see this progress in price. In fact, it's pretty in a very good trend. In fact, for the micro LED TV in terms, so that sound like they do have ways to overcome all the technical difficulties. In terms of micro display, eventually we want to wear them for eyeglasses, Google display, this type of thing. People trying to pursue for virtual VR display. We think a full color is still challenging because now the pixel we would like not to be like 3 pixels on side by side. You want to have higher resolution. It's preferred to have stack them up. So that's a difficulty still need to overcome for micro display part, we think. Yeah. It's not fully overcome yet, but a lot of progress for the red color based on indium gallium nitride.
Could you tell me a little bit about those challenges in terms of color? You mentioned red, and I know blue has been notoriously difficult with a lot of LEDs.
This related with energy band gap of this material. You start with gallium nitride. It's a little bit on the UV side, and then you add some percentage of indium, you get the blue color. And then you add more indium, you get to the green color. So for the red color, you have to add a lot of indium. But the indium nitride on the indium gallium nitride on the indium nitride side, it's very difficult to control. But there's a lot of progress, use different methods. You can put more and more indium inside of this system. So now you get the red emissions with enough efficiency or at least close to the and green color. So now you can combine these three together. So in terms of the full color, it's already a lot of progress. Now the question is, how do you put these three colors together and use some kind of mechanism to drive them? Not only each pixel, you also have the three colors. And so that part also needs to be overcome. But I think this can be done and probably will be done in a few years.
Probably mechanism still will remain as CMOS driving each pixel, but how do you drive the stack, the pixels? Maybe need some kind of thinking there. So which some of the bigger companies probably they have some ideas already. Yeah, as long as the fundamental physics part is already overcome, yes, in terms of color control stuff.
Right. Now we've touched upon this a little bit, but with micro LEDs, it seems manufacturing is notoriously challenging, and from the sounds of it, rather lengthy. The issues of thermal mismatch, the sapphire substrates, testing, replacing the faulty LEDs. They all seem to be sort of creating like the perfect storm for a costly product. And some of my information may be a little bit out of date there, but that said, prices, as you mentioned, have come down a bit on those displays. Can you tell us a little bit about some of the progress that has made that happen?
And one of the most important progress in terms of making these micro LED large TV, it is still is the how to transfer these and micro LED from the wafers and to the large panels. And in the beginning, I think a few years, and the company they've tried to find the way and basically to improve this called mass transfer technique. And a lot of progress, and now I saw the news, and there's some company they even have the equipment designed purposely to do this job. And a lot of progress, but still need to even and transfer more efficiently. There's another way approach is interesting, and I saw there's some publications. And what you do is you put a little bit of magnetic materials inside this micro LED, and then you have the array of the magnets underneath. So you just randomly pour all these micro LED on the top surface, and then when they start to get to the place you want them to be. So this is a very smart idea, and this idea it was adopted from an early time from the semiconductor concentrated solar cells, and developed to a certain point. And now it's coming back, and you just want to put the old LED in the right place. So in principle, if you have a magnetic array, can control them to the right place, and then be much easier. Just pour in all the micro LED, and they will kind of slide into the position. But of course, and this still need to be and developed for the real production. But there are some publications already pointing, and there are some positive results by approaching this way.
Well, I would like to add, I would say, it's really for the industry to take this technology over for mass production wise, I would say the history is not that long, right? You think it's like started like 2001. So now it's not that long. They are making a lot of progress already. So we think it's going to be coming down, just like other technology TVs we saw, like OLED has been like out there for 20 or 30 years, and eventually now we see the TV price coming down, right? So this would happen, same thing to the micro LED TV as well, we think. So maybe give another few years, we think the price probably will come down. We all willing to buy by then for ordinary families. Yes.
Sure. Now you had mentioned with the magnetic thing. Is that Does that refer to the panels going into place?
Yeah, these are for
To
the micro, the large TVs.
right,
So
right.
as the work shows up, you put a little bit of magnetic materials, and then you underneath you have a magnetic arrays, and then it's much easier and to put these micro LEDs to the periodic structures, the place you want. And I think if this can be adopted to the production eventually, then this will be a very effective way, because assuming you can imagine you have these small magnetic array, you can turn on, turn off. You pour in all the micro LED randomly, and then you turn on the magnetic field, and then they get to the right place, and then you turn off your magnetic field, and then you can move this to the next step and repeat the process. So you don't have to transfer one by one, and these micro LED become smart. They know where they should go.
So I suppose right now they're just using pick and place, right? Right now they they use mechanical arm, like a robotic arm to pick one micro LED, put in right place, do it really fast right now. That's why the cost is still relatively high. But imagine like some technology, as Hongxing was mentioning, if you can mass transfer millions of LEDs at one time, then price eventually for the big TVs will come down dramatically. Then maybe give them another few years. Yeah.
Right.
Right. Yeah.
How has progress in related or adjacent technologies such as liquid crystals, quantum dots, MEMS, and others? How has that helped to facilitate the growth and adoption of micro LED technology?
I think if you look at the history from the LCD display, and then now we have the quantum dots, now we have the OLED, and you look at all the specific and the numbers, and they become brighter, and resolution become better, and the color becomes more colorful, and so they're kind of pointing to what is exactly we call the perfect display should be. And now people use a terminology called the ultimate display should be. And you look at these all the specific numbers, and you imagine that you're pointing to, and now this micro LED display will be probably the perfect display. And in terms of everything, in terms of the speed and the brightness, resolution, So this helped the two people to get why this micro LED technology is so important. And particularly as some of the technology, and they cannot be adopted for the emerging technology, like AR, VR, and these are there are some limitations. But with all the specs we know from these blue, green, and red indium natural micro LEDs, and we don't see any shortfall or any limitations for all these emerging applications. That's why and people all get excited.
Yeah, I suppose you could you imagine the lighting, how bright it is. So now we are talking about the display application. Obviously, the lifetime, for example, is much more. You couldn't compare with LCD or like even OLEDs or any other technology. Lifetime is much longer. You can actually make them much brighter and also self-emissive. You don't need any backlight. And the angle, we call that, this is a wide range of, you can go to the side to look at the TVs. It's still very bright. You don't have this problem of like, the angle, it's went down. It's really bad viewing on the other side. So we have very wide view. It's all seems like there is no, as Hongxing pointed out, we don't have shorter falls from micro LED technology. So as you were saying that whatever the technology previously before that, so we have some kind of wish list of what we could have, because we are something limited in terms of lifetime, something limited in self-emissiveness, brightness, resolution. So you look at basically, there's a wish list of what we wish to have. Micro LED can give you all that. That's the reason probably it can fill in. Yeah, nothing could be better. That's what people think.
Excellent. Now, I was wondering if you might be able to talk just a little bit, kind of briefly about some of your current work with micro LEDs. Is there anything right now that the two of you are working on in the lab that you're excited about?
We still have some thoughts in how these full color micro display and can be achieved with the progress on the red color side. But we have some idea in the designs. One thing is, and when the bigger company and start to involve to make these become real products, and then we need to find something it's unique, because I think the bigger company can do a lot more, a lot better in terms of how to bring a device from the concept and to the production eventually for the mass in the market.
And we do have some new technologies and based on like emerging from this micro LED idea, for example. I mean, we recently just have some allow the patents or issue the patents on like we call the phased array technology, optical phased arrays, which it is based on our like a micro LED idea. We drive them by CMOS, where we could actually eventually make these things out of like a electronic counterpart like a radar, but we can make a LiDAR out of micro LED arrays. So that's actually patents are issued. So that's a new technology we're trying to really, it's actually coming out from a research lab at university, but it's not really to a stage of mass production yet. But there's some new concepts people are actually exploiting. Not only our lab, there are other university labs trying to use, actually many publications, right? How to use micro LED for some new applications, yes.
Excellent. That's really interesting. Could you tell me a little bit about, what might some of the advantages be of using, a micro LED for LiDAR, for example?
For what?
For LiDAR.
For LiDAR. Oh, yeah, that's something we developed. These days, used to be the early time you have a radar is rotates all the time, mechanical part. So of course it's become not so robust. And later on, people developed called the phased array. That's for the electrical magnetic way. You can scan the sky without any moving parts. So there's no such a thing for the short wavelengths on the optical wavelengths. So it has been a very significant question about almost 30, 40 years now. Can we control a light beam in the visible wavelengths without the mechanical part? And that's work done and more on the one-dimensional scale. And now we have a two-dimensional array, and we just need to control the index reflection, control the phase of each pixel, and we can control the light reflected back from this we call the optical phase array to any direction in a 2D and plane. So we spent quite a lot of time and working on that, and we have some positive results. And this could be quite interesting because now, in order to control all these pixels, you need to have the size of the pixel close to the half of the wavelength. So for the visible wavelength, now we're talking about each pixel down to the 300 nanometer. So 20 years ago, as that cannot be done because with amount of information, you don't even have a computer power to control this kind of amount of the pixels. But now it is not a problem. How do you achieve this phase control for each pixel with this kind of small size? It's a really nobody did anything like that. But for the longer wavelengths, it's a lot more easier because the wavelengths become bigger and pixels become bigger. But this is just very beginning, and we find that there's a lot of work can be done in this field.
Yeah, maybe take another 20 years. It's just like our micro-LED initially become this late, but that's just like a original ideas but it's related to micro-LED, the array idea. So it's based on 3 nitrides. So, but as Hongxing mentioning, I mean, for visible arrays, this is the pitch requirement is really comparable to wavelengths. It's become even more challenging than the micro-LED technology for display, in fact. Yeah.
For example, if you look at this self-driving car from Tesla, and at the top there is something is rotate. Yeah, look at this one. Something is not right. Okay. There's a mechanical part. You have a car driving. You have all these rotates. So what happens? Something happens. So we need to have one device
chip
that can look around, and all the time there's not any moving part. That is the optical phase array device. So this, I think eventually this can be done with current and all these nanotechnology or nanophotonics, this kind of thing. So we're also very excited about that technology. You can control the light without any moving parts.
There are some ideas already. People, you might heard of phased array, optical phased array. Typically, something realized is in 1D, one-dimensional. Now, for the array LED, we already automatically have 2-dimensional array. So that's still a chip size. You can put on the car without even notice there's anything, but without requiring any like a radar, like a rotating on top of something. So that would be very interesting, but it's gonna take another 20 years to be realized.
And one more thing is people working on this one-dimensional phase array, and most approach is using use a temperature change. Temperature change and resulting the index reflection change. But this effect is very small, so typically you need a very long optical path. And it comes up, and we work on micro-LED from these gallium nitride materials. And these nitride materials, they also have a very interesting property in terms of how to control index reflection, how to control the carrier concentrations. So that's how we decided, and this is the direction and we should pursue.
Yeah. Mm-hmm.
Excellent. It's funny you mentioned 20 years. I used to do, so in photonic spectra, we have, what is it called? We look back 5, 10, 20, and 30 years ago at previous issues of our magazine.
Yes.
Yeah, right.
And a lot of times, when we get to the 20-year mark, we're looking at technologies that are just now getting commercialized.
Okay.
So I just thought that was kind of a...
Yeah, I think some of them even now takes even longer because we're getting to more and more complex things. Just like micro-LED, it was first of all demonstrated 2000, so rate 23. And the commercialization right now still is very small and in terms of market size. But as you said, it takes a long time. And yeah, we're very, very appreciative with your magazine and report a lot of our work early time. And one thing we found very recently, I think about 6 months ago, you mentioned that 20 years ago. And 20 years ago, we developed another photoluminescence technology can look at the aluminite wavelengths at 200 nanometers. That's what we call the infrastructure important. At the time, we work on the gallium nitride. And aluminite photoluminescence is not that easy to be measured. So we would like to work on the aluminite 200 nanometer UV wavelengths. So we thought about this one. Eventually, we developed one called the time-resolved picosecond system, which can do the time-resolved photoluminescence all the way down to 200 nanometers. Now there's products and many groups now can look at the time-resolved luminescence all the way down to the 200 nanometers. So all these kind of...
Exactly, yeah. Your Photonic Spectrum magazine, December issue last year, says 20 years ago. There's
Kansas State.
Yeah, we were at Kansas State. That was like some memory or whatever. History, development, photoluminescence system characterizing semiconductor aluminum nitride. That was interesting. You put it back, so that mentioned that technology, but I thought, wow, you guys didn't mention about the micro LED. Also like 20 years ago, right?
Right.
But it's good that you come back and say you want to interview us. That's interesting. You did report our work. I went back to 23 years ago for micro LEDs. Yes.
As you mentioned, 20 years kind of time frame,
Yeah.
and almost this is the time for the deep UV LED.
Yeah.
Deep UV LED, the basic property for the aluminum gallium nitride was also around the 2000. But really, these deep UV LED become products, I think, around the 2018 sometime, So it takes that long, but now we have very good deep UV LEDs now.
Yeah, it's sounds like 20 years it's kind of normal from a concept to really like a product, useful products, especially for hardware technology. Maybe I'm not talking in behalf of like a software technology, right? All the hardware technology seems like 20 years is needed to really go from concept to real products. So for now, the micro LED display technology by itself, the market size predicting is reaching like 30 billion by 2030, according to some of the market research agencies. So it's really satisfying for us as an academic and professors.
Excellent.
Yeah.
Now, I guess sort of the elephant in the room, so to speak, is that the two of you are husband and wife. How long has that been the case? And what's it like working together? Both in the lab and at home. Say for example, like washing the dishes.
Yeah, I guess we try to balance like first of all, we are very grateful to Kansas State University. They probably one of the first institutions are willing to hire husband and wife in the same department, which was really a traditional was forbidden. I guess they willing to do that. That was really a big thing. So we are grateful. So we feel blessed. But we find in the beginning we did fight each other. It's not that as you were saying. At home people still struggling who's going to wash the dishes, right? So we find pretty soon we kind of look into our working on our strengths, which part we more efficiently we focus on. So the part we're good at. So we complement each other, and we feel that's more efficient. In fact, more than two people, because if the part we are bad at, we don't emphasize. We focus on our strengths. So that's actually we do same thing in the lab at home. For example, Hongxing really not enjoy washing dishes, so I would let him pass that. But he likes to cook, so I enjoy cooking. So he takes over some of those duties. So at home, that's what we we do. Yes, yeah.
And it's not only we work together for so many years. In fact, and we were trained together. I'm 2 years older than Jingyu, but we were the same lab, so in the graduate school, and we share the same advisor. Yes. And so it's a very unique experience. Work together for almost 40 years. And I think other than what Jingyu said, the one thing I feel interesting is we have a lot of the kind of casual and very enjoyable and conversations, either at home during the dinner or even go out at dinner. That's probably a very unique experience, because typically, I suppose most husband and wife, we're not talking about business, talking about some problems. But these kind of moments, you kind of enjoy the dinner, and you kind of relax. But sometimes you have something coming up, and they have people talk about to kind of more finalize your question and where is really problem and helps down the road. And when these kind of things happen quite often, so I think it really helps us to in many aspects, which kind of problem we should attack, and how to prepare, how to attack these problems. I think that's very unique experience, and so far we are very enjoyed this procedure.
Yeah, that's true. I guess we talk more, even talk work all the time, basically, which, yeah, I mean, sometimes we met the students in restaurants, they say, oh, you guys actually eat? Yeah, we do eat, But while eating, we do also can talk about the ideas, generating new ideas. It is very, it's a unique experience. Yeah, we enjoyed it. Yes.
That's excellent.
Yeah, thank you for asking that question. Really makes us look back. This is, it is very enjoyable. Yeah.
No, it's wonderful. It's wonderful to hear about. It's not often, on All Things Photonics that we get to, talk about something like that. So, it is very nice. I want to thank you both so much for for appearing on the podcast. This has been such a great conversation. We're really looking forward to it.
Okay, thanks again for the invitation. We also very enjoyed. Okay, thanks a lot.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.